Hello, everyone. So last time we were looking at the solutions of higher order ODEs. Higher order ODEs, and we saw the steps to solve or find the general solution of an equation of the type y nth derivative plus, let's say, cn minus 1, yn minus 1, all the way to, let's say, c1 y prime plus c1 y prime plus, let's say, c0 y0 equals 0, c0 y equals 0. And we saw the steps were finding characteristic equation, and then finding roots of characteristic equation, and then finding linearly independent solutions using roots found above finding linearly independent solutions using roots found above based on whether we have real or complex roots, and based on multiplicity. For example, we saw that if you have a real root, simple real root with multiplicity 1, let's say if r equals 5, then e to power 5x would be one of the solutions. If you have, let's say, a real root with multiplicity more than 1, for example, 5 and 5, then e to power 5x and x times e to power 5x will be the linearly independent solutions corresponding to those roots. And similarly, if you have complex roots, let's say alpha plus minus I beta, then we can consider e to power alpha x sine beta x and e to power alpha x cos beta x as linearly independent solutions. All right, let's look at an example. Find an ODE such that y1 equals e to power 2x cos 3x, y2 equals e to power 2x sine 3x, y3 equals e to power 5x, and y4 equals x times e to power 5x, and y5 equals e to power 6x are the solutions of that ODE. So I think I also mentioned last time that we can have two types of questions in this topic. Either the ODE is given and we are asked to find the linearly independent solutions or general solution, or it's the opposite. Maybe the solutions are given or the linearly independent solutions are given and the ODE is asked. So in any case, if we know the connection between the solutions and the ODE itself, Then we can solve the question. So the connection is through the characteristic equation. So if the ODE is given, we have to find the characteristic equation, and then we can find the roots, and then we can find the solutions. Also the other way around, if the solutions are given, we can find the roots. And from the roots, we can find the characteristic equation. From the characteristic equation, we can find the original ODE. So here the solutions are given. So let's find the roots of the characteristic equation. So this answer or the solution, first, find the roots of the characteristic equation. What are the roots of the characteristic equation? Well, we have e to power 2x cos 3x and e to power 2x sine 3x as the solution. So that means the roots are 2. The root corresponding to these solutions are 2 plus minus 3i. Because again, remember, we just mentioned that if you have alpha plus minus I beta as roots of your characteristic equation, then the corresponding solutions will be e to power alpha x cos beta x and e to power alpha x sine beta x. So here alpha is 2 and beta is 3. So we have R1 and R2 equals 2 plus and minus 3i. These are the roots corresponding to y1 and y2. Then corresponding to y3 e to power 5x, we have R3 equals 5. R3 equals 5. Corresponding to y3. But we also have x e to power 5x. So that means 5 is a repeated root. Again, everything that I'm saying is based on the table or the remarks that we mentioned last time, that if you have simple real roots, what should we do? If you have repeated real roots, what should we do? Simple complex roots and repeated complex roots. We said for a simple real root, just if the simple real root is Ri, then e to power Rix. But if it's repeated real root, then e to power Rix, then x e to power Rix, then x squared e to power Rix, and so on. So here we have e to power 5x and x e to power 5x. So that means 5 is a repeated root. How many times is it repeated? 2 times, because we have e to power 5x and x e to power 5x. If we also had, for example, x squared e to power 5x as another solution, then that would mean the multiplicity is 3. But right now, the highest power of x is 1. So multiplicity is 2 here. So R4 is also 5. Again, corresponding to Y4. And finally, Y5 is e to power 6x. So I must have a simple real root corresponding to this solution, which is R5 equals 6. All right. So then I found the roots of the characteristic equation. Then I need the characteristic equation itself. So this is something you learn in pre-calculus, that if you have the roots of a polynomial and you want to find the polynomial itself, what should we do? Well, we know that if x equals a, let's say, is a root for my polynomial, then x minus a is a factor for my polynomial. So basically I have all the roots here, so I can find all the factors. And based on that, I can find the original characteristic equation or characteristic polynomial. So next, we will find the characteristic polynomial using the fact that if x equals a is a root of p of x, then x minus a is a factor for p of x. From Math 100. So here we have all the roots, therefore we can have all the factors. So p of x will be, or let's say p of r, because normally we use r, letter r instead of letter x for the characteristic polynomial. So p of r will be r minus, so what are the first two roots are 2 plus 3i and 2 minus 3i. So r minus 2 plus 3i times r minus 2 minus 3i. And then we have two roots of 5 and 5. So r minus 5 and r minus 5. And we also have r5 equals 6. So r minus 6 corresponding to r5 equals 6. That's it. So this is, I had 5 roots, and r minus those would be my factors, and I just need to multiply those factors. And let's see what we get. So this is, if I simplify the first two factors, it's going to be r minus 2 minus 3i, r minus 2 plus 3i, r minus 5 the whole squared, r minus 6. Now, for the first two factors, I can use the identity a minus b times a plus b, which is a squared minus b squared. So this one I can write it as r minus 2 the whole squared minus 3i the whole squared times r minus 5 the whole squared times r minus 6. And then this is r minus 2 the whole squared minus 9i squared. I squared is minus 1, so minus 9 times minus 1. R minus 5 the whole squared times r minus 6. And then this is r squared minus 4r plus 4 plus 9. R minus 5 the whole squared, r minus 6. Which is r squared minus 4r plus 13. R minus 5 the whole squared, r minus 6. And if we expand this further, we'll get r squared minus 4r plus 13 times r squared minus 10r plus 25 times r minus 6. And if we simplify, just a simple algebraic simplification, just expand and simplify. then you will get r to power 5 minus 20 r to power 4 minus 6r cubed minus 698 r squared minus 1055 r minus 1950. So this is basically my characteristic polynomial. Why do I call it characteristic polynomial, not equation? Because I still don't have equation. I just wrote a formula for my function. If I put this equal to 0, then I can call it characteristic equation. So the only reason that I'm calling it polynomial is that I haven't set it equal to 0 yet. But once I set this equal to 0, then I'll have my characteristic equation. So our ODE will be of the form, we can basically form it using the coefficients that we found for characteristic polynomial, and the powers have to be replaced by order of derivatives. So our ODE will be of the form y fifth derivative minus 20 y fourth derivative minus 6y third derivative minus 698 y second derivative minus 1055 y prime minus 1950 y equals 0. So this will be our ODE, which we found it using the characteristic polynomial, and just replace powers with order of derivatives, and we use the same coefficient. So this is the ODE with the given solution. So this ODE will have the solutions that we needed. This ODE has y1, y2 to y5 as its solutions. But our y1 to y5, its only solutions, they are not its only solutions, because we know if y1 to y5 are linearly independent solutions for our ODE, then anything of the form c1 y1 plus c2 y2 to c5 c5 y5 is also a solution. So the general solution for this ODE will be c1 y1 plus 2 c5 to y5. But y1 to y5 basically are the linearly independent solutions for our ODE. Now we want to look at non-homogeneous ODEs. So far we looked at homogeneous ODEs. Now let's look at second order non-homogeneous ODEs. So let's say if we have y double prime plus p of x times y prime plus q of x times y equals f of x, with f of x not equal to 0 this time. If f of x is equal to 0, then we call it homogeneous. But if f of x is not equal to 0, then we call it non-homogeneous. So a theorem, any solution of the equation above, of the ODE above, can be written in the form of y equals yc plus yp. So I'm going to explain what yp denotes here and what yc denotes here and what yp denotes, where yc is a solution of homogeneous equation y double prime plus p of x y prime plus q of x y equals 0. And yp, so this yc is called complementary solution. That's why we call it yc, called complementary solution. And yp, called particular solution, is an arbitrary or let me say is one solution for the non-homogeneous equation y double prime plus p of x times y prime plus q of x times y equals f of x. So if we find one particular solution for our non-homogeneous ODE, then we can find all the solutions, because any solution can be written of the form yc plus yp. So basically, what does this theorem do? This theorem tells us that, well, we want to find all solutions of the non-homogeneous equation, all solutions. But let's say if we can find one of the solutions for this non-homogeneous ODE, which we can call it yp, a particular solution, then we can find all the solutions using that particular solution. How? We just need to add this yp, the particular solution, plus yc, where yc is the homogeneous solution, the solution for homogeneous equation. And we already saw in the previous parts how we can find the solution for homogeneous equation. So let me write it in other words. Let me write it another way. If y1, y2 are linearly independent solutions of the homogeneous equation, y double prime plus p of x times y prime plus q of x times y equals 0. And if yp is a particular solution for y double prime plus p of x times y prime plus q of x times y equals f of x, then the general solution of y double prime plus p of x times y prime plus q of x times y equals f of x can be written as y equals c1 y1 plus c2 y2 plus yp. So we want to know the general solution of this equation. Let's assume we have one of the solutions called yp, a particular solution. That one solution can be found using guessing or using other methods that I will explain later. But let's assume we have one of the solutions for this equation. And then we can find the general solution very easily. How? You just need to add that particular solution with this solution of the homogeneous part, the general solution of the homogeneous equation. General solution of the homogeneous equation, we already saw how to find it. This equation, we saw that if y1 and y2 are two linearly independent solutions for this equation, then the general solution for this equation can be written as c1 y1 plus c2 y2. So we just need to add that solution, that general solution with yp, and then we get the general solution for this ODE. So if I want to summarize, if this is the if you have a homogeneous equation, to find the general solution, just find y1, y2, the linearly independent solutions. The general solution will be c1 y1 plus c2 y2. If you don't have homogeneous, if you have non-homogeneous, still you need y1 and y2. In addition to that, you need one particular solution, which we will explain later how to find it. Then you can write the general solution as c1 y1 plus c2 y2 plus yp. And this c1 y1 plus c2 y2 is also called yc, complementary part, the general solution of the homogeneous equation. Yp is called particular solution. It's just one of the solutions for the non-homogeneous equation. So let's see why. Let's look at the proof of this theorem. So suppose that, let's say ys is an arbitrary solution of y double prime plus p of x, y prime plus q of x times y equals f of x. So I'm considering an arbitrary solution. And then my goal is to show that this ys here can be written as c1 y1 plus c2 y2 plus yp for some c1 and c2. Because I want to show that any solution can be written of this form. So, and ys is an arbitrary solution. So I need to show that ys can be written in this form. All right, now let's look at ys minus yp. Our claim is that ys minus yp, this ys is some function, yp is also some function, yp is a particular solution for this equation, one fixed solution, and ys is an arbitrary solution. Now, if I look at the difference between these two functions, my claim is that the difference between these two functions satisfies the equation above. let's see y. So ys minus yp double prime plus p of x times ys minus yp prime plus q of x satisfies the, let me say, equation above. I mean, the homogeneous version. So satisfies, let me write the equation. Satisfies y double prime plus p of x times y plus p of x y prime plus q of x y equals 0. So this will be equal to 0. Why? Because ys minus yp double prime plus p of x ys minus yp prime plus q of x times ys minus yp can be written as ys double prime plus p of x times ys prime q of x times ys minus ys double prime p of x times yp double prime p of x times yp prime q of x times yp. And what will be this? So if you look at the first expression, the first three terms together, because you know what did I know about ys? I knew that ys is a solution for this equation. So that means ys double prime plus p of x ys prime plus q of x ys will be f of x. So the first three terms can be replaced by f of x. And similarly, yp is also a solution for this equation. Ys and yp are both solutions for this equation. Yp is a fixed solution that we could found it by guessing or some other method, just one of the solutions. And ys is an arbitrary solution for this equation, but both of them are solutions for this equation. So that means if I replace y with ys, then I'll get f of x, or if I replace y with yp, again, I'll get f of x. So this is f of x minus f of x, which is 0. So we showed that ys minus yp satisfies this equation, and this is the reason. So we can say ys minus yp satisfies y double prime plus p of x times y prime plus q of x times y equals 0. But we know that any solution of this equation, this is the homogeneous equation. We know any solution of this homogeneous equation can be written as c1y1 plus c2y2. We know that any solution of this homogeneous equation can be written as c1y1 plus c2y2, where y1 and y2 are linearly independent solutions. And ys minus yp is one of the solutions of this equation. And any solution can be written as c1y1 plus c2y2. So what does that mean? Well, that means ys minus yp can be written as c1y1 plus c2y2 for some constants c1 and c2. So ys minus yp equals c1y1 plus c2y2. And then ys will be equal to c1y1 plus c2y2 plus yp. And that's what we wanted to show, that an arbitrary solution can be written of this form. C1y1 plus C2y2 plus yp. So to solve a non-homogeneous ODE, we need to find y1, y2 linearly independent solutions of homogeneous equation, homogeneous ODE, and also we need to find yp, a particular solution. So there are a few methods to find yp, a particular solutions. So methods to find yp. The first method we want to explain is a method called undetermined coefficients. So in this method, we guess a form for yp based on the given f of x this form includes some coefficients and we will find those coefficients by substituting yp into our equation. So there are some coefficients, undetermined coefficients that will be involved, but we'll find them by substituting into the equation. And how can we guess the general form? We guess the general form based on the given function. So for example, if the given function is exponential, our guess will be exponential. If the given f of x is trigonometric, our guess will be trigonometric, and so on.